This is an overview of the Molecular Models Lewis Structure worksheet. Let me show you how you fill out the columns. It tells you that there are actually up here, tells you there are 4 columns that you need to be filling out. And so let me take you through those 4 columns. It also gives you some rules about the way you do the calculations, but I'll go ahead and describe those to you down here. So the molecules formula is given on the left that you're trying to find the structure of. We draw the skeleton here, and the rule for the skeleton is basically take the central atom and then connect it to all the non-central atoms once. And then we do the calculation of the valence electrons and the formal charge calculations. Now, formal charge calculations could be either done in this box or they can be done over here. So let me go ahead and go through this. I drew the skeleton, then the valence electrons. Well, there's 1 phosphorus, and each phosphorus has 5 valence electrons, and there's 4 hydrogens, right? And each one of those has 1 valence electron. That's a total of 9 electrons, but we have to take into account the charge, so I'm going to subtract 1 because a positive charge means you lost an electron. So it's 9 electrons minus 1 electron. That leaves me 8 valence electrons for my structure. Now I need to look to see how many electrons are drawn out already in the skeleton. So I have 1, 2, 3, 4, 5, 6, 7, 8, or that is counting each electron in the bonds. Remember, bonds are 2 electrons. Or you can simply say there are 4 bonds, 2 electrons per bond. That's 8. That leaves me with 0 remaining electrons because it's going to be 8 minus 8. If you need reminders of how to do some of these simple calculations anyways, it's all up in here. Okay. But this is the method I want you to follow. It's essentially what's done in the lecture. Now, what's left is to calculate formal charge. This is actually just a reminder to say, did you calculate the formal charge on phosphorus? And once you do it, you can put an X in it or not. But we'll go ahead and do the formal charge of phosphorus. Phosphorus has 5 valence electrons. And what we use as a formula is this right here. It says valence electrons minus 1/2 the bonded electrons. So the bonded electrons are these ones, 2, 4, 6, 8. So that's going to be 8 over 2. And then we have to subtract off any lone pair electrons. Now, if you look at this structure, the way it's drawn, there's no lone pair electrons, so I'll subtract 0, and that's going to be plus 1. So phosphorus has a positive formal charge, and the hydrogens don't have any formal charge, and you'll learn about how you tell that for an atom in the lecture. But since hydrogen normally makes 1 bond and it has 1 bond, typically that's a situation where you have 0 formal charge. Now, this one's fairly neatly done. You need to recopy it neatly here. This is just all the scratch work. And you'll see for some of the later ones, you do a lot of fiddling around with the structure. I don't want to see all that fiddling around and try to grade it. But I do want to see a nice clean structure on the final Lewis structure column. And you do need to check formal charges for particular elements. So like this one says formal charge is selenium, and ask whether or not this structure obeys the octet rule. Okay. Now, when we're counting electron groups, the following things, I'll just draw it at the very top of this column, count as 1 group. A single bond for sure counts as 1 group. A double bond, though, and a triple bond, and a lone pair, these are all representative of 1 group. Each is a group. So a triple bond doesn't count as 3 groups because the triple bond is all on one side of an atom. So when we say electron groups, it's really the number of groupings of electrons that we find around the atom. So in this case, we could count this, right? That's 1, 2, 3, 4. So we have 4 groups. We have no lone pairs, and this really refers to lone pairs on the central atom. Now, if you don't have a double bond, typically you don't have any possible resonance structures. It is still possible in the case of incomplete octets to have resonance without a double bond already present, but if there are none, then you just write 0. That is, if you can't draw two structures, then there are no resonance structures. Resonance structures requires a minimum of 2, so go ahead and drop a 0 in there. And this doesn't say not applicable down here. Originally, the way this was set up, you're just supposed to put yes or no here, and then how many were down here, but I just decided that we would go ahead and put in the number of structures, 0 meaning there are no resonance structures. So now we'll take a look at phosphate ion and draw it from scratch and look at resonance structures and possible Lewis structures for this compound. So to begin with, we need a skeleton, and so we'll put phosphorus in the middle. And I have 4 oxygens, so I'll go like this. As a general rule, symmetry is not a bad idea, although sometimes it can be difficult. But for all the polyatomic ions, one atom, generally not oxygen, goes in the center. And then we'll count up valence electrons. So phosphorus, again, has 5, so it'll be 1 times 5. And then I have 4 oxygens, so that'll be plus 4 times 6. And then it has a -3 charge, but let's go ahead and calculate this out. So this is going to be 24 plus 5, so this is 29. And then we need to add 3 electrons for the charge of 3 minus, and then we end up with 32 electrons. Now, in our skeleton, what we have is we have 2, 4, 6, 8. So there's 8 skeletal electrons, or you can simply say 4 times 2 because there's 2 per bond. And so the electrons that I have remaining to distribute are 32 minus 8, or 24. Next, we have to distribute the 24. And I by far prefer to distribute these as lines. So I'll go ahead and say like this, 24 divided by 2. And then I would end up with 12. And then I would distribute 12 lines like this. But I'm going to go ahead, because it can be confusing for students, to take just 24, at least when you're first doing these. And I know for many of you this is the first time you're doing this. And I'll draw 24 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now, having said that it's evenly distributed, I can see as I'm filling it up, I'm getting octets. The other thing to be aware of, something that people will often do in their heads, is say, well, I have 4 atoms, there's 24, so I put 6 per atom, and then they just go through and really quickly do the dots. So far so good. What we've done is we've done valence electrons, skeletal electrons, remaining electrons, distributed those on the remaining atoms. And then what we have to do is take into account formal charge. So I'm going to do it for oxygen here, and then I'll do it for phosphorus. Okay. So for oxygen, again, the formula is valence electrons minus half of the bonded electrons minus all the lone pair electrons. So just as a thought, you should keep in mind that half of the bonded electrons is simply the number of bonds, because each one has 2 electrons in it. So you can very quickly write oxygen should have 6. It has 1, subtracting 1 for the bonds, and then subtracting 6 for the lone pair electrons. We count every single one of those, and that's a -1 charge. Now phosphorus should have 5, but it has 1, 2, 3, 4 bonds, and what I end up with is a formal charge of +1. And again, going all the way back up here, I'm just following this formula of valence electrons minus half of the bonded electrons minus lone pair electrons. And just note, I also put the little note here, half of the bonded electrons is actually the number of bonds. That's a totally acceptable way to do this. So, when you see that, then what you have to recognize is that you can minimize the formal charge by removing a pair of electrons from here and then putting a double bond between the oxygen and the phosphorus. So now we have to recalculate the formal charge, and so we'll put a line through it like this. And so phosphorus, this is going to be 5 minus, and then 1, 2, 3, 4, 5 bonds, minus 5, that's 0. And then for the oxygen, it's 6 minus 2 minus 4, that's also 0. Now, having said that, right, this one became 0, this one became 0. Notice there's 3 other oxygens that follow this calculation, and so this one's -1, -1, and -1. Again, a quick rule is that if you add up all the formal charges, it equals the overall charge. So now that I've done all this kind of work over here, you can go ahead and write it out neatly on the other side. And then I'm going to choose to draw the lines that I prefer to do. And then it's an ion, and what you'll learn in lecture is for anything that has a net charge, then what you're going to put brackets around it like that to indicate it's an ion. Now, we've checked the formal charges of oxygen and phosphorus. Does it obey the octet rule? And the answer is actually no. All the oxygens obey the octet rule, but phosphorus, in forming this double bond to remove some of the formal charge, actually violates the octet rule with 10 electrons. So 1, 2, 3, 4, 5 times 2, so that would be the 10 electrons. Again, it can do that because it has d orbitals to play with. Oxygen can't actually violate the octet rule because it doesn't have any d orbitals to play around with to place the extra electrons. And then finally, we have to decide on the number of electron groups. So if I was doing this, I might use a highlighter and say, well, I've got these electron groups. So I have a total of 4 electron groups. The double bond, like I said before, and it's very useful actually to write this at the top of the column to remind yourself that each one of those could be counted as one group. So there are 4 electron groups, and then there are no lone pairs. And I know that seems strange at first, because you can see all these lone pairs on the outsides, right? But we're only asking really about lone pairs on the central atom, and so there's 0 lone pairs. Now for the question of resonance structures. Remember, resonance structures indicates the number of ways you could have written an equivalent structure without moving atoms. So you can only move electrons, and if you look, right, we put a pair of electrons from this oxygen to satisfy the formal charge requirement. Well, we could have done that for any oxygen. So the number of resonance structures is 4. And then again, ignore that line. Originally, it was resonance structures was supposed to be a yes or no, and then I decided could answer that with the number of resonance structures as well. So hopefully that clears up for you how you do this. Again, if you have any questions, feel free to ask.